Welcome, everyone. My name is Siggi Gíslason, and I'm the President of the European Association of Geochemistry. Collaboration with other scientific societies is key to building a strong geochemical community. Therefore, it is an honor to have 4 societies present their awards at the Goldschmidt conference. I first would like to welcome Wei Dong Song from the Sensu Song Foundation to present the Sensu Song Award. Please come to the stage.
Yeah, thanks. I'm Wei Dong Song from the Sensu Song Foundation, and it's my great pleasure to be here. The Sensu Song Foundation is designed to recognize young scientists who work in mainland China, Taiwan, Hong Kong, and Macau. This year's Sensu Song Award goes to Chuanzhou Liu. So I know Chuanzhou more than 15 years ago when I was a postdoc in Max Planck with Professor Hoffman, and Chuanzhou went to Mainz as an exchange student from the Chinese Academy of Sciences. It turned out he did a very good job with many good papers, including article paper in Nature and Geology, many other papers. So he's well recognized in China. In 2013, he got the first Excellent Young Scientist Award in China. That's the start of Excellent Young Scientist Award in China, and he and several others together get that award. So let's welcome Chuanzhou Liu.
I now would like to welcome Jacinta Ensweiler from the International Association of Geoanalysts to present the IAG Young Scientist Award.
Thank you for introducing me. The International Association of Geoanalysts promotes the advancement of geoanalytical science and supports the professional needs of those involved in the analysis of geological and environmental materials. One way of attaining our goals is stimulating the career of young scientists. Each year at Goldschmidt, the IAG dispenses the Young Scientist Award for excellence in analytical geochemistry. Eligibility is limited to scientists who are currently pursuing a higher degree in a field related to geoanalysis or who have completed their university education within the past 5 years. I wish to thank the organizers for the opportunity to present the award during this ceremony. We are now accepting nominations for next year's award. Martin Claver is the recipient of the 2019 Young Scientist Award in recognition to his contribution in applying the double spike technique to improve the accuracy of isotopic composition measurements. I am pleased to welcome Martin to receive this prestigious certificate.
I now would like to welcome Michael Carpenter from the European Mineralogical Union to present the EMU Research Excellence Medal. Please come to the stage.
Well, good morning, everyone. My name is Michael Carpenter, and I'm here in my capacity as President of the European Mineralogical Union. And I too would like to thank the organizers of this meeting for allowing us to present our medal at this meeting. And also, our medalist gave a brilliant lecture on Monday afternoon. The EMU Research Excellence Medal is presented to an early career scientist who has made significant contributions to research in mineralogy and whose professional and society activities contribute to strengthening scientific links in Europe. And it is my pleasure and privilege to present the medal for this year to Dr. Katharina Marquardt.
Finally, I would like to welcome Nessus Otero from the International Association of Geochemistry to present the IAGC Award.
Thanks for the introduction. It's really great to be here. Bon dia to Tom. Good morning to everyone. So I'm here as a president of the IAGC. I will present 3 of our numerous awards, and we also are open for the 2020 awards. The first award is the IAG Fellow 2018. It's bestowed annually to scientists who have made a significant contribution to the field of geochemistry, and it's to Jochen Hoefs from the Georg August University at Göttingen. Of course, all of you that work on light stable isotopes have seen his stable isotope geochemistry book, and he has published almost 200 papers related to that topic. So. So the next award that I'm going to present is the IAGC Edelman Award, which is bestowed biannually for a geochemist of particular merit and outstanding promise that is less than 35 years at the year of nomination. And it's for Julien Boucher from the Institut de Physique du Globe de Paris for his contribution on the geochemistry of the critical zone and his work in the link between stable isotope fractionation and the balance between chemical weathering and physical processes. And our last award is the IAGC Bernatsky Medal 2018. And I'm sorry of those of you that were not, because you just missed a really nice talk. And it's the Bernatsky Medal is awarded to a single person for a long time career dedicated to geochemistry. And I would just take the words of Sigurdur that nominated the person. The awardee is Jacques Schott from the Centre National de la Recherche Scientifique in Toulouse, and it's for a lifetime of insightful experimental investigations in mineral-fluid interactions, and because the body of his work has been instrumental for characterizing weathering attenuating waste transport, and the past environmental record on Earth.
And now, my great pleasure is to introduce today's plenary lecturer, Dr. Alissa Park. She is the Lenfest Chair in Applied Climate Sciences of Earth and Environmental Engineering and Chemical Engineering at Columbia University. She is also the director of the Lenfest Center of Sustainable Energy at the Earth Institute. Her research focus is on sustainable energy conversion pathways with emphasis on carbon capture, utilization, and storage. Current efforts include the fundamental studies of chemical and physical interactions of natural and engineered materials with CO2, such as the development of novel nanoscale hybrid material for combined CO2 capture and conversions, and the investigation of carbon mineralization schemes fixing CO2 into solid carbonates. I heard first of Alissa through Wally Brooker a few years ago, and he spoke highly of her intellect and energy. In a short time, she has started a large research group at Columbia, and she is one of the founders and directors of the Gordon Research Conferences on carbon capture, utilization, and storage. I'm very much looking forward to your talk. Alissa, the floor is yours.
All right. Thank you very much, Sigi, for your kind introduction. I was very surprised when I got an email from Helen to come and give a plenary talk at Goldschmidt's. First question was, what is Goldschmidt's? And geochemistry? And then I said, you do know that I'm not a geochemist. I said, oh, that's why we want you. And then later I found out there was a Sigi behind this whole operation. I said, oh, now I understand. So as Sigi mentioned, I have a connection to Wally Brooker, and this is the photo I like to show. Elizabeth sent me this photo, and I think this is one of the photos they really, really loved. As many of you know, Wally Brooker was at Columbia University, our colleague, and he's a giant in geochemistry, and he passed away early this year. And I think it was a big loss, but at the same time, personally, it was a big loss for me, because for me, he was not only a colleague, but more like a father. So I lost my father 8 years ago, and there was time he just declared that he will be my new father. We had a lot of puzzle games, Sunday night dinners, and I think I learned a lot from him beyond just geochemistry. Actually, we never talked about geochemistry, more about life in general, and I really loved it. There are a lot of photos of him and me and my family, but I wanted to show this photo when he looks really charming. And hopefully he's watching over me, and he always hated wearing tuxedo, but he did for one night, and it was really nice. So what do I want to talk about today? I'm a chemical engineer by training, and I do chemical engineering, but I have a really unique opportunity as I joined Columbia 2007 that I had wonderful colleagues at Lamont, which is only like 40 minutes away, and I found out that they're fascinating people. For example, Peter Kellerman sitting right there, and then he'll walk into my lab and say, oh, you have a serpentinite, you have this and this and this and that. I'm like, what? So what I don't like is the heterogeneity in my samples, because I need to do quality control, I need to do controlled experiment. So what do I do with that wonderful rock? I grind like hell and make it into powder so they will be always consistent. But my geochemistry colleagues, they bear with me, and then we had a wonderful collaborations over the years. So today, I'd like to tell you a little bit about our collaboration, but also I'd like to tell you something about chemical engineering side of it, how we actually capture CO2 from various power plants or steel plants and cement plants. So let's see. So I'm not going to tell you about climate change, and I think there's a lot of climate change modeling people in the audience, and they can do a lot better than me in prediction and what has even happened. So let's not go there. But at the same time, about 2013 and 2014, in the United States, we had a lot of discussion. After 2 decades or more of a serious funding and significant effort, why don't we have CO2 capture and storage implemented yet? That was tough question, because generally when we say in chemical engineering, to commercialize any chemical technology from conceptual idea all the way to commercialization, it takes about 2 decades. So now we don't have any more excuse. We did have 2 decades. What happened? So it was tough, but at the same time, these 2 reports came out around that time. And I think this was the IPCC, and this is a National Academies report. We were a little worried that these reports will say, well, it's really too late, it's just a big problem, so let's not even bother with it and skip it. But in fact, what they said was, we need substantial multi-century climate change commitment created by past, present, and future emissions of CO2. It seems like a very simple statement, but it's not when you think about it. So as an engineer, environmental engineer, when you say, oh, my chemical plant makes something really dirty, what would I do? I'll go to your chimney and say, well, if it's gaseous emission, maybe I can install something to clean up that mess so that nothing goes out. Which means that by doing so, we can definitely address maybe future emissions and maybe a little bit of present emissions, depending on how we do it, how fast we do it. But how about these little words called past? So if it's solid waste, like garbage, you know exactly what you did with them. Either it's in the garbage can, or in the landfill, or in the environment, which we don't want. But how about carbon dioxide? What have we done with these? So when you think about it, a lot of times people say, which is not a good thing to say, is the best way to deal with pollution is dilution. Hopefully we don't continue to do that. So we diluted this carbon dioxide into atmosphere for many, many, many years. So what happens is, although we complain about global warming, increased CO2 concentration, it's only 400 parts per million is diluted into environment. So going back to historical emission of CO2 and picking them up is not very easy thing to do and big challenge. But the fact that this report said this means that we are committed, we are serious, and we need to do more than just zero emission, but we need to go even negative emission technologies, and this is a big challenge. So in a way that by saying this really scary statement, we regained our energy. And in fact, after COP21, this happened. The ministries of the different countries, I think now it's 23 countries and EU got together and then formed Mission Innovation for accelerating the clean energy evolution. What they said was, not only internationally, we need to collaborate in big-scale projects and then actually demonstrate the technology, but we also need to advance science. What they're saying is this is urgent problem, but it's not going to be just for the next 5, 10, or 15 years. It means that we really need to advance the fundamental science to get there for our future generations, not only one generation. So what they wanted to do was double up at least the fundamental R&D budget by double. Do you feel a lot of funding nowadays? I don't know. I don't feel that much in the United States, but that was the whole idea. So with the idea of climate change, they came up with 7 ideas. Now we added 1 more. So 7 ideas were you need to have a smart grid and all that other things, so way beyond how to harvest solar energy and all that so on. And the last one was added 2 years ago or so is hydrogen. But if you look here, the one I want to point out is there is CCUS, carbon capture, utilization, and storage. And if you look on the right, these are the countries committed to different topic areas. So let's look at the CCUS. basically most of countries are quite interested and committed to CCUS. And interestingly, United States and Saudi Arabia were two leads at the time. And I think about 2 years ago, United States stepped down as a lead, and now UK is leading it right now. So what they were asked in these 8 areas was that have a workshop with all the important people, thought leaders in the world, and then let's think about what are the big scientific questions we need to ask, which means that we were asked not to develop the roadmap, it was a vision statement. So I was involved in CCUS workshop, which was held late fall 2017, and this report came out 2018, I believe. So you can access it online, and this is a really good way of looking at what's the big questions people are asking in CCUS areas in fundamental level. So going into the carbon capture, utilization, and storage, at the beginning we called it carbon sequestration, and it got a little confusing because carbon sequestration was mostly referring to carbon storage, so then we started calling it CCS, which is carbon capture and storage, and then we added U in the middle, which I'm gonna talk about a little bit later on. So if you have a power plant, which we usually focused on at the beginning of CCUS research, there's a coal-fired power plant emitting a lot of CO2, that's the point source. How do we capture CO2 at high quantity? And that was a big challenge. And even 2 decades ago, people thought that it was really, really urgent problem. So what we were told, or I guess it was before my time, so that carbon capture people and storage people have to work really hard. And when you look at it, I think some of you are in the storage side, but most of you are not in the capture side as much, I think. So there are a lot of chemical engineers, material scientists, and maybe chemists in the capture side, and geochemists, geophysicists, and maybe civil engineers on storage side. And what we were told was that somehow or another we'll transfer CO2 from one side to the other. And what people were asked was, what's happening in between transportation was that if you have pure CO2, so that you can minimize the amount of CO2 you need to transfer, and you have to dehydrate it because you don't want to have any water in your CO2 system. And if you can pressurize it about 150 bar, you can move them around in a pipeline, no problem. So capture people were asked to capture CO2 and compress it to 150 atmospheric pressure, and storage people were asked, let's now inject. So if you look at this chart right here, this is the Department of Energy coming time to time, publishing what are the technologies out there. So this is the ready for demonstration versus this is the cost reduction benefit. So obviously, they think that these are more futuristic technologies versus these are the more newer, the known technology. And in fact, amine-based CO2 capture solvent are really well developed. Initially, those amine-based solvents were developed for sour gas cleanup. So when you have H2S from your methane natural gas systems, you can separate them very easily. So we had a lot of know-how starting from there. So we thought that, well, CO2 is acidic gas, we just need a base, why don't we do that? So if you look at the reactor system, which I'm much more familiar to, this is a reactor system. Generally, CO2 capture is using 2 reactors. First reactor is here, and then CO2 containing flue gas will go in, and flue gas usually 15 volume% of CO2 when you burn coal. And then you can put the solvent, and then you can capture CO2 by taking CO2 out of the flue gas. And basically, what you're doing is separating CO2 from nitrogen. Okay? And it's just acid-base reaction. And after that, CO2-loaded solvent will go to the second reactor. Now we call it solvent regenerator. And there, now you need to put the energy in. Because when you do acid-base reaction, energy-wise, you're going downhill. Now, in order to spit out the CO2, you need to put energy in. And that energy can be either temperature swing, or pressure swing, or both, and many other things you can do. But you still have to pay energy. So what happened was, if you have really strong base, like a strong binding energy, capture is very easy. Your capture reactor will be very, very small. But at the same time, you have to put huge energy penalty to go back up. compared to if you have a binding energy very weak, your reactor, which is right here in green one, will be really big. At the same time, energy required to kick that CO2 off again, it'll be very small. And once you kick off the CO2, then you have to recycle back the solvent, because you're not going to use solvent once and throw it away. So people have been developing this for a number of years, and in terms of reactor, where it fits into the power plant, is that after the boiler, after you remove the sulfur, and then CO2 capture, and that's how usually it's designed. So we do have these in large scale, thankfully. So we weren't the first one. United States was not the first one built the large-scale CO2 capture plant, unfortunately. It was Canada. But we have one in Houston area called Petronova Project. And this is the picture I took with my iPhone in 2017. This is a CO2 capture unit, and this is a CO2 solvent regeneration unit. You see how big these are. This is not even a full scale. So the size of the reactor you have to build is huge compared to even sulfur capture unit. Going back to this technology, as I mentioned, when you try to capture CO2 and regenerate the solvent, you need energy. So if you're in the business of making power and energy, where would you get energy to do that operation? The additional reactions you have to do, right? So what you have to do is either you burn more coal, or you have to reduce your power plant capacity. So people did a lot of calculation for a decade. And what they estimated was, if you want to capture significant amount of CO2 in this power plant, you will reduce the power plant efficiency by 1/3. So I guess you're not in the power plant business, right? In the United States, our power plants are very old. In average age, even older than me, so very old. So then, with that age, their efficiency is like a 34%. So if you're reducing power plant efficiency by 1/3, which is 34%, we are getting to the very, very low number. So people are getting frustrated, and they start asking, why is it so low? One of the reasons was because these solvent materials cannot be used as a pure component. You need to dilute it in water. So maximum concentration is maybe 38%, which means that we have 70, 85% of water going along the ride. So you have to heat it up, all that water, cooling it down really quickly, heating up, cooling down a large amount of water very quickly. And you do know heat capacity of water. It's a very, very expensive process. So we still have to do this because we know this process very well, and that's why we are building large-scale CO2 capture systems based on amine-based solvent. We'll continue to do it, and we need to understand how to minimize energy penalty, how to do the heat integration, material integration, so that we can do better. But at the same time, a bunch of us in the academia start thinking that, well, if we like amine but don't like water, can we make new materials without any water inside? And these are water-lean or waterless CO2 capture materials. I'm not going to go into too much detail, but there are materials like ionic liquid, similar to like molten salt, but under 100 degrees C. So in room temperature, it looks like kind of honey-like material, very unique. And it doesn't have a vapor pressure, so that you can heat it up to 120 degrees C and then cooling it down without worrying about any of the fumes coming out. Fumes are very, very hard to deal with when you make a chemical process. But I was looking at this ionic liquid, and it's really unique and nice, but I really didn't want to make all this ionic liquid. It takes a lot of organic synthesis. So what we ended up doing was working with Lyndon Archer at Cornell University. We developed a new system called NOMS, which is nanoparticle organic hybrid materials. Basically, in simple way, what I'm saying is we put liquid polymer tethered onto nanoparticle. By doing so, you can really improve the thermal stability. And as you remove the water from the system, you can make waterless or water-lean system, which has very interesting CO2 absorption behavior. Because all these hairs, which is now attached to polymer chains attached to nanoparticle, it wants to be relaxed by having small gaseous molecule go incorporate into their polymer chains. So we made a whole bunch of these. Initially, when you talk about enthalpy effect versus entropic effect, always enthalpy effect is a lot higher. So we wanted to look at the materials without any amine function groups yet. So when we did that, definitely we improved the thermal stability by 100 to 150 degrees. This is the untethered polymer, and this is tethered polymer, which means that now we have 100 to 150 degrees more window for me to do a lot of these chemical processes and operations. If you do it only once, that doesn't work, because in order for us to make economical process, initial cost of the solvent has to go into the noise of your operating cost, which means that you should be able to run your solvent many, many times. So we did up to 100 cycles, seems to hold up very well compared to untethered polymer. So chemistry is exactly the same for the polymer. Only thing we did was we plugged them onto, tethered them onto inorganic substrate, which is nanoparticle. So we wanted to see whether did we change any structure change, because that was our hypothesis for our entropic effect. So if you look here, you don't need to look into detail, but this is 2D rosy NMR. This is untethered polymer. This is tethered polymer, our material, and you see a lot less signal. And analyzing this signal, basically what it's telling you is that when you tether your polymer, liquid polymer molecules onto the nanoparticle, they get stretched out, and they get stretched out. So that you increase a huge amount of free volume where you can jam-pack CO2 along the way. So now, only thing we had to do was just decorate them with a lot of amine groups, and then that's what we did. And as you can see, more bases we added, like red ones, we have huge boost in CO2 capture capacity as we expected. This all sounds good, but this is how academic research, right? We write really nice, interesting papers and all that, but when you think about it, going back to the photos I showed you, we're not going to make 1 milliliter at a time and try to think that we're going to capture CO2 from a coal-fired power plant. So the question becomes, can we make this in tons and tons quantity? And if we do, how do we going to feed these materials into each reactor and move them around? So one of the first things you have to ask once you make novel materials is the viscosity. So we start looking into viscosity, and this is the temperature versus viscosity, and this is the amine-based solvent, which is like a water-like consistency. It's very easy to pump it around and spray trickle bed reactors. Reactor design is very, very simple. But if you look at ionic liquid, these are the sum of the ionic liquids, and these are our NOMS materials. It was quite high up, and then also it was quite depressing when I realized this was a log plot. So I didn't know what to do. So I looked at my students and go, okay, well, there's no way for me to try to move honey around the big reactors. That doesn't make any sense, because it will take a lot more energy to do anything. So high viscosity creates two major problems. First, you can't move them around between reactors, CO2 capture unit and solvent regenerator. Second, interfacial phenomenon, mass transfer between gas phase to liquid phase will be very difficult, because it's really hard to create bubbles or droplets of these. So we started thinking about how to address this issue. And not only us, ionic liquid people were addressing the same problem. There are many things we can do, including changing a lot of chemistry. You can change the intermolecular hydrogen bonding network and all that. We can do all the fancy things, which I'm not going to talk about today. But one thing I do like to talk about, quite interesting, was encapsulation. We started thinking and working with the Lawrence Livermore National Lab. They said that if we have very sticky stuff, can we just chop them up and then keep them apart by packaging them? We thought it was a really crazy but interesting idea. So that's what we did. We created the 3D printing of this interesting microfluidic device. And what we did was, our sticky CO2 capturing material is blue in color, and white is the UV curable polymer. And what we did was we made droplet instead of droplet in these systems. And after that, we do UV curing. Now you have UV cured shell encapsulating this fluid which captures CO2 without any water. So we thought it was really interesting and nice idea, because now this shell may be able to selectively reject water while letting CO2 in. This is gas permeable. And it did. So we made, these are some of the photographs of actual materials we made. So instead of worrying about really high viscosity fluid, now you have 300-400 micron size particles We know how to deal with particles very easily, and these never going to dry up because their vapor pressure is almost negligible. So looking at here, we can do multi-core and single core. We can also control the thickness and all that so on. One of the reasons I got really excited about this particular material is because of this. I don't know whether you were at the talk by Klaus Lackner yesterday, and he's one of the good friend of Wally Brooker, and they've been talking about direct air capture. How can we capture CO2 directly from air? Remember, I started my talk with talking about that little 4-letter red word called PAST, and this is one of the many ways you can capture CO2, which is historically emitted. So Klaus has been developing this system which can be passively standing in the environment, picking up CO2. And what I was hoping that these new materials we developed, we can incorporate into this system and then use to pick up CO2 from the environment. Another ways to capture CO2 beyond amine is you can actually capture CO2 at high temperature. So high temperature CO2 capture is somewhat more close to what you're used to in terms of reaction. There are some technologies called chemical looping technology. And these are interesting because it's kind of mimicking natural process. So there are two systems. One is carbonation-calcination cycle, and the other one is oxidation-reduction cycle. First one is basically what it's doing is it makes limestone and burning the limestone and making limestone and burning the limestone. Basically, that's what we are doing. If you start with the limestone, maximum conversion you can have is only 30%. So we do have to engineer the sorbent, the material itself. Or you can do oxidation and reduction cycle, which is quite interesting, and a lot of research is going on here, which what it does is that using metal oxide like iron oxide, instead of burning your fossil fuel using oxygen or air, you're burning it with metal oxide. So by doing so, here, you are burning the material and any carbonaceous material and make CO2, which is sequestration ready. At the same time, oxygen is delivered from steam or air by solid oxygen carrier, and once it's reduced, going back to pick up another oxygen. By using this chemical looping, you can actually have CO2 capture inherently embedded or actually pick up CO2 at high temperature. So what would you do once you capture CO2? That's a big question. If you care about climate change, you have to store. You definitely have to store. We make way too much of CO2 to convert to anything else. So if you care about climate change, we have to store as much as possible. But there's one little area, utilization, a lot of people are getting really excited to, and this is the one area I often ask to give some insight into. This is the US Department of Energy's version of what can we do with CO2 once you make. Don't try to read all these details, but you can find it on their website. Basically, they're saying you can make anything you want which has carbon in it. So look around in your room, in this room. It would be hard to find any material that does not have carbon in it. So when you think about it, you can decarbonize the power sector. Can we decarbonize the chemical sector? No, right? If there's no carbon, there's no material, right, or chemicals. You can only defossilize the chemical sector, maybe. So there's a lot of questions people have been asking. One of the first areas people do in terms of utilization is using as a working fluid, which we've been doing for a long time. I think many of you know enhanced oil recovery. You can recover more oil out of the ground using carbon dioxide injection, which is tertiary recovery of CO2, crude oil. Unfortunate side of this whole picture is that more than 80% or close to 80% of CO2 being used for enhanced oil recovery in the United States is natural ones. We actually go to naturally stored CO2, mine them out, and then use it to take more hydrocarbon out of the ground. Is it good for the environment? Definitely not. So one of the first thing we should do, low-hanging fruit, is that replacing that natural CO2 using capture CO2. But there are many other things you can do. If you care about converting CO2 to something else, should we capture it to pure CO2 and compress it to 150 bar? Maybe, maybe not, depending on what your reaction is requiring. So you have to ask the question, what requirement for CO2 as a feedstock for various reactions? And also, we have to ask, what are the scale of these options? If you look here, there's a fire extinguisher and dry ice versus the fuels. Definitely, they are not in compatible size in here. So you have to think about, if I want to convert back carbon dioxide into something else, what should we make? Those are the big questions. So a lot of us work on liquid fuels or even chemicals, and that's one of the areas. In a way, in chemical engineering or chemistry field, we knew how to reactivate carbon dioxide into interesting materials. But we did not do that until now because we did not have carbon-free energy. If we burn something down to low energy level, to push it back to high energy level material, you need carbon-free energy, and we didn't have that for a long time. And interestingly, our renewable energy installation is a lot faster than we thought. Great news. But at the same time, our energy storage installation or capacity is a lot less than we thought. So there's a mismatch. So for the first time, there's a renewable energy research group and CO2 group kind of had a common theme or a common interest. Because renewable energy people want to store their renewable energy, even for not only for hours or days, but months and seasonal. Then you really need a high energy density material, which we know is a hydrocarbon. So they said, well, if I give you a lot of carbon-free energy, either as a heat or electron or hydrogen, can you do something? And that's where we started. You definitely need better catalyst. You need to have good catalyst to make whatever we want to make. At the same time, we need to have a co-reactant which is very sustainable. There are 4 different colors for hydrogen: black, gray, blue, green, and we wanted a lot more green or even blue hydrogen. Without that, we cannot really claim that we did something good for the environment. So depending on, this is for example of electrochemical conversion of CO2, depending on how many electrons you pay or protons you feed, you can make different chemicals. And there's no question that we can do this. But the question is, if I ask you, there's a jet fuel from crude oil, there's a jet fuel I just made from captured CO2 from industrial source, and then hydrogen from splitting water, and we have a whole bunch of renewable energy, and I made another jet fuel. Which one is greener for the environment? I'll give you a simpler question. There's a paper cup versus plastic cup. Which one is greener? The answer is depends. Unfortunately, let's say if I give you, instead of a system boundary of just a cup versus cup, I'm going to give you a little bigger system boundary, including us and environment. If I tell you that this paper cup came from cutting down the last tree in tiny African city or village, and then flew with Air Force One and bleached like hell and made that paper cup. At the same time, plastic cup I recycle locally with plastic bags. And I'm going to use this particular cup 1,000 times before I throw it out. I'm being really extreme. And this paper cup once and throw it out. Now I'm asking you again, which one is greener? Unfortunately, instead of like Coca-Cola, we can have a calorie value at the back of the bottle. This is not a simple question because it's path dependent. So understanding what is the right size system boundary to discuss this, whether we did good for the environment, is very important. So going back to this story, carbonates are very interesting, and that's why many of us are working in this area. Among all the conversion pathways, this is the thermodynamically downhill. And in fact, a lot of know-how is built in this area because of our CO2 storage effort in the past. And this is a famous Sally-Benson's plot showing that if you inject CO2 into the geological formation, you'll go through different storage trapping mechanisms. And one of them at the end is a mineral trapping. So only if you have reactive geological formation, you might even make carbonates. Wouldn't it be great? And that's a lot of people start working into. And not only that, going back to this plot, people really like the idea of maybe we can even make materials. So talking about scale, among all the little bubbles you saw, what are the top 5 products can you make from carbon dioxide? If you have unlimited amount of energy, of course, that's the question. And these are the top 5 materials in terms of annual revenue. Concrete, fuels, aggregates, polymer, and methanol. These are the 5 materials you can definitely make. And I think we are quite familiar with concrete and aggregates, in inorganic carbonates and all that. And if you convert this into, I'm really interested in how much carbon we can put it into product itself or avoid it. And this is the potential reduction in CO2 emission, exactly same analogy, but for the same materials. Top 5 is still top 5, but order changes a little bit. So if you look here, aggregates are the ones you actually make solid carbonates and put it into construction materials, compared to concrete is just securing the concrete using CO2 environment. Either way, this has really good potential to put away a lot of CO2 in short term. So let's look in here. Where are all these minerals? There are many, and I think you guys know more than me where these are, which is a good thing. And I think a lot of my colleagues, and Peter and Jörg, goes to Oman quite a bit because they have really interesting geology, and we should learn from it. And in fact, Peter keeps saying, just do this in your reactor, why not, right? So we actually have good results, and Siggi was part of this, and Martin as well, is that Karfix project in Iceland, they injected CO2 underground where the geothermal energy is being harvested, and then looking at how basalt may react with CO2 over the time. And kind of going back to this plot, you see one of the things you may notice that there's no years or numbers, because there was a lot of debate. Is it going to be 2 years, 100 years, thousands years, or millions years? We don't know. It really depends on a lot of things. So we were wondering how fast this reaction going to happen. And there are 2 tracers who were added. One is carbon-14, and also CO2, and also SF6. And by looking at the difference, we start to realize that, oh my gosh, there's a lot of CO2 not coming out when SF6 does. Means that some reaction may have happened. Wouldn't it be great? And in fact, they did find these crystals in less than 2 years that fresh carbonates being formed. So somehow or another, even in situ case, you can actually push your environmental system, a geological system that formed this solid carbonate. But as a chemical engineer, it's really hard to use Earth as a reactor. It's not easy to mix them, it's not easy to do anything with them. So I thought that, well, there are a lot of materials I can carbonate, but maybe some of them I can even mine them and then do ex situ carbonation. So these are some of the examples of materials and minerals you can carbonate, or rocks. These are the basalt and other materials, which is large in quantity, but less concentration of calcium and magnesium. Obviously, you don't want to mine those materials to put as much CO2 as possible, but there are materials like wollastonite and other serpentine and olivine, which has much higher magnesium and calcium concentration. Those we can put energy in to mine and do a lot of carbonation in the reactor system. If you look at in nature, there are a lot of complex reactions that are happening in carbon mineralization. So CO2 in gas phase or supercritical phase has to be hydrated and speciated into different species in water phase. At the same time, for example, magnesium silicate material like serpentine has to leach out the magnesium and make carbonates. The leaching of magnesium is favored at low pH. Making carbonate, solid carbonate, is favored at high pH. So it gets complicated. So if I, as a chemical engineer who wants to have fastest reaction kinetic and also largest conversion, it's much easier if I decouple them. So we actually use 2 separate reactors for leaching of magnesium and carbonation. When you look at actual reaction itself, there are a lot of research been happening because you're really pushing this reaction to the 100% conversion. And what we found out was conversion is very limited because as you react, there is a silica leach passivation layer formed. So in nature, maybe Earth doesn't matter, but for us, we want to minimize the reactor size. It means that every single particle, mineral particle we add, we need to have almost complete reaction. So we start adding chemicals. So there are 2 types of ligands we put in. We were hoping that if we have magnesium targeting ligand, and then there's a silicon targeting ligand, kind of working with each other, maybe either they can peel them off so that we can make sure that the thickness of this ash layer will be minimum, or maybe it does something else. And as we added and then did the reaction, mixture of catechol and oxalate, for example, did really great job, sustained a really good leaching behavior of magnesium from serpentine. And only reason it went down at the end was because we ran out of stuff to dissolve, which was nice. And what we found out was particle size never changed. So as if that, what happens, the reprecipitation of silica as we leach out the calcium and the magnesium was not impacting the pore structure in the ash layer. In fact, the overall particle size remained the same, but it was almost like making the bigger highway, so that we did not have much mass transfer limitation. So now we knew how to dissolve this material very quickly in the reactor system. We need to carbonate them. And based on thermal, we thought that, well, we should make magnesium carbonate. And then we looked at a whole bunch of literature review, and it was all over the map. And apparently, there are many different phases of magnesium carbonate, especially at low temperature. And what we were told was that magnesium has a lot thicker hydration shell compared to calcium, which we were more used to, that because of that, at low temperature, you always make hydrated phases of magnesium carbonate, nesconite, hydromagnesite. So we were puzzled, and we didn't know what to do, because the reason is, as we can see here, that at higher reaction temperature, we definitely make anhydrous magnesium carbonate. At low temperature, you make a lot of materials with a lot of water attached. But in terms of process engineering, we want to minimize water being attached to your product, because your product will be much heavier. You'll be losing a lot of processed water. So we were trying to see that, can we push this reaction temperature down? Because higher the reaction temperature, again, more energy you need to put in to do the exactly same reaction. So one of the things we tried was, can we start with the seeds? And these seeds may have different chemistry. So some of them had anhydrous magnesium carbonate, and the other were more inert type of material. And interestingly, when we did the carbonation in these systems, all cases, we always made hydrate phases, except when we started with magnesium carbonate, even at moderate temperature, we were able to make anhydrous magnesium carbonate, which was quite interesting. So what was the overall process? What we had is this. You can start with a material like an olivine or serpentine or elastonite, and you have two types of reactors. You can leach the magnesium, and then you can also have CO2 bubbled into secondary reactor, and then have third reactor making extra carbonate. Which I didn't get to talk about is we can use an enzymatic catalyst called carbonic anhydrase to accelerate hydration of CO2, which is, after making all these possible, now bottleneck was dissolving CO2 in water. So after that, we thought that this is great, but still, is it economical? There was a lot of questions. But one last bit I want to tell you about is that because all the things we learned, right? We started because of carbon mineralization, because of CO2 storage. We did with the mineral carbonation ex situ. And if you're going back, one of the interesting things is because it's a chemical process, we actually have reactors, we can separate materials as a product, actual product. So a lot of industries came to us, especially steel industry. If you look here, this is how much CO2 storage potential is silicon material and seawater, huge, as we know. It's far beyond how much coal we can burn. At the same time, there are industries much smaller, which is the steel industry and aluminum industry and coal-fired power plant. They are both CO2 point sources. At the same time, they have a lot of solid waste, which is with high alkalinity. If you look here, China versus Germany, don't look in detail, but look at the yellow part. China has a lot of yellow, Germany does not, right? Yellow are the amount of slag going into landfill. So now we have opportunity to solve a solid waste management problem with CO2. So we work with China a lot these days and looking at how to convert these materials, slags, into carbonates. And these kind of look like minerals and rocks, right? So understanding the mineralogy of these materials is very interesting, and how to design even better design steel plants to have better mineralogy for future carbon mineralization is very important. So kind of connecting to geochemistry and engineering side of it. I think there are a lot of interesting intercept between geochemistry and chemical engineering or even engineering at these days. Not because of CO2, but also beyond in terms of recovering unconventional resources. This is one example of recovering rare earth elements and metals from slags, industrial waste. We also do, using CO2, recovering metals from electronic waste. There are a lot of things. Now we have to re-ask question. We had really good ores for many, many years for us to have built all our modern infrastructure. If we have to redo it, and if we have materials which is highly engineered stuff, how do we work with them for the future? So in summary, we need to consider all the CO2 sources for the future, and solution cannot be single source. We need to have a wide range of sources or solutions working with each other. Mineralization is challenging. I see that all the time. And there are a lot of questions. We need to ask them together and answer them together. But at the same time, it has great potential for many different ways, not only for climate change, but also resource recovery, as well as built environment and infrastructure for the future. In order to do that, we need to somehow connect the chemical reactions with the transport behavior in many different heterogeneous systems. And I believe that for future, if we're going to stop using fossil fuel, we have to think about how to create new pathways to existing chemicals, but not only that, even new pathways to new chemicals. And at the end, technology should be developed considering our environment being inside the system boundary. These are my students and all the funding agencies, and thank you very much for listening, and I'll be happy to answer any questions.
Thank you very much, Alissa. Do we have questions? Well, while we're waiting for a question, I would like to ask you a kind of a political question.
Sure, really?
What do you think of the prospect of, if we're not carbon neutral by 2050, and there's a lot of overshoot, what is the prospect of direct air capture? Do you think we can do it? Is there enough energy for us to do it? Do we have the technology to do it? And will it be done?
Okay. So how many of you are familiar with direct air capture? Oh, quite a bit. Good. So for those who doesn't understand what direct air capture is, as I mentioned, you can actually capture CO2 directly from air. And that has been challenged for over the years because if you have 15 volume% from coal-fired power plant versus 400 ppm in air, you know which one is easier. But there are two questions. If you're asked, there are two rivers with fish, right? And if I'm asking you, fish as many fish as possible, where would you go? The one with the lots of fish, right? But if we are saying not only we go to zero emission, but we're going to go even negative emission, let's fish out all fish out of both rivers. Both are hard. So when you think about it, which one goes first? And a lot of people in the argument at the beginning, let's do easy ones. And don't do the hard ones until easy ones are done. But at the same time, as I told you, when you talk about technology development, it takes 2 decades. So if you do one thing at a time, we're never going to make it. We need to have many, many solutions. So interesting thing about direct air capture is most of these are designed as a modular, maybe 1 ton a day kind of system. So what happens is that when you do CO2 capture in power plants are big energy utility companies. So only they can play the game, or the partners who can collaborate with them. But when you talk about direct air capture, a lot of people, if any of you, can get into the market and start doing it. And I think that's why it got not commercialized, but being demonstrated a lot faster than people thought. And same as CO2 utilization. Although we should not be converting CO2 to something high valuable until we store a significant amount. But at the same time, we are doing it at the same time. So in terms of timing, I definitely believe direct air capture will be a lot faster, not because of political will, it will be more market-driven. And because you can see the impact so quickly, compared to waiting to build the million-ton, really large scale, takes many, many years to build. So I think we'll be doing both. Hopefully we do both.
Yeah.
Any questions? Yes.
Please go ahead. You have to shout.
Definitely. So the
Could you
question,
repeat?
yes, the question was, is there potential to using zeolite as a material for CO2 capture? Oh, definitely. There's a lot of research going on in zeolite area. Whether we're going to use natural zeolite, I think so. Unfortunately, in academia, a lot of us always like to make new things. So we had a lot of research going on MOF, metal organic frameworks. This is more engineered version of zeolite, kind of, right? So there's mesoporous materials. There's a huge amount of research going on. Whether MOF, this metal organic framework, gonna be used for CO2 capture, I think so. There is challenges, but zeolite, I think we should really look into zeolite. At the end of the day, because of the scale of it, unless you can get it from nature and maybe a little bit of doping and things like that can really help, we should definitely look into zeolite.
Last year, there was passed a federal law in US providing $50 per ton of CO2 if you inject it into sedimentary basin.
Yes.
Do you think that's going to make a major difference?
In United States, 45Q you're talking about. So kind of going back to policy. So as you may know, what's happening in the United States. We don't talk about climate change as much, although interestingly, we do talk about CCUS without talking about climate change as much, which is interesting. So even considering our political situation, we have a new tax credit. So we always had a low carbon fuel standard in California for a number of years already. We now have something called 45Q. So if you store CO2, then you get $50 per ton credit. If you utilize, you get $25 to $35 per ton credit. And that was one of the reasons a lot of CO2 utilization started to get pushed into the tech to market a lot faster than people thought. And same as direct air capture. So it's a kind of interesting time. Would it help? Definitely. When you look at any technology development, in especially environmental technologies, there are three things. You need to have a policy. Without any policy, why would anybody do environmental control? Unfortunately, we don't, right? Big companies would not. At the same time, if you have market pull, and you definitely need to have good technology, all three has to work really hard, work with each other, then we can get to the environmental control much faster.
We have a question over there.
Yeah, so I'm really fascinated by the utilization side of this. And this might have something just to do with what you had time to talk about or just what you had chosen as sort of areas of interest. But it seemed to me that there was kind of two sides of things we talked about. It was utilizing carbon into some sort of form that again would be released into the atmosphere as carbon dioxide, or making carbonates, basically. And is there any sort of other utilization that you have sort of high hopes for, or are those kind of the two main directions that seem like they would be at all useful?
Great question. So there are four main areas. So when I did the mission innovation workshop in CO2 utilization, there's so many products we can make. So what we did was we divided the panels into four of different pathways, conversion pathways. So first one is the thermochemical conversion of CO2, basically using heat to convert CO2. And in fact, a company like Covestro in Europe, they are making mattresses, polyurethane out of CO2. And then there's the electrochemical, photochemical, artificial photosynthesis, which I kind of briefly talked about. Third one is inorganic pathway, I also talked about. And then there's a biological pathway. Biological pathway is interesting. Some of the companies like LanzaTech, they went down to like a near volcano area and find bugs, which lives on not photosynthesis, but lives on high energy gas. So like hydrogen, methane, and those things. So what they're doing is they're teaming up with industries like a steel plant, using their waste gas, feeding it to biology, like bugs, with CO2 and making biofuel. There are many different things. But good question about the permanence issue. Definitely. So kind of I told you about the life cycle analysis issues based on the paper cup versus plastic cup. It's really important to see the system boundary. So if your system boundary is making only fuel, it looks good, right? But if you make it even bigger, including the combustion of that fuel back into atmosphere, then you have to do bean counting very differently. So when we talk about the $50 per ton or $25 per ton tax credit, or even developing this technology saying, do we do any good for the carbon footprint for the environment, you have to include, your system boundary has to be big enough. So more permanent solutions like utilization, like carbonate, which has good permanency, of course, it will get a lot higher carbon credit compared to which is holding on to it just a little bit as making fuel and recycling back and forth, which needs to have a direct air capture that will have very different scheme of counting carbon credit.
We have a question from Peter Kielman here. Peter, you just have to shout. I will repeat. Repeat.
Investments in direct air capture.
Yes.
Why did they do that? And is it a good idea?
Well, I actually get funding from Shell to do direct air capture, so even Shell goes into the pile. So I don't know, maybe a good example would be Saudi Aramco, in my opinion. So Saudi Aramco has one of the biggest reserve on petroleum. At the same time, they do invest in direct air capture. I was puzzling why. So when you think about your company gonna last only next 10, 20 years, who cares? But if you think that your company will last forever and long time, one day you may not be able to use fossil as your product, right? So the question becomes interesting. In Saudi Arabia, they have huge potential for solar energy, right? So now you have an option. You have all this petroleum at the same time solar energy. Then once I have a solar energy, I can make it into electricity or heat, especially electricity, let's say. Then I have an option of running the transmission line to Africa and Europe and sell electricity. Yeah, you can do that. But the problem is electricity doesn't store very well. And they already have a huge infrastructure working with hydrocarbon. So in a sense that we do not like fossil fuel, but it does not mean we do not like hydrocarbon. So I think a lot of energy company or oil company want to be in hydrocarbon business because moving this high energy density material around is very nice. And we developed this whole infrastructure and we came to this conference because high energy density of fuels and chemicals. So being able to utilize that is very important for them and I think important for us as well. So as long as we can still use high energy density material without having huge carbon footprint would be good. So in order to do that, if you want to close the loop, you need to have direct air capture. So only way get the CO2 back out of the air will be either photosynthesis or direct air capture. So I think it is future. Can we do it in 10 years? Maybe not in the scale we want. In the many years now down the road, hope so.
Yep. Could you repeat the
Yes, he said that air to fuel is analogous to corn to ethanol. That's what he was saying. Okay, how many of you heard of corn to ethanol? Most of you. Do you think it's green technology? Nobody thinks it's green? We thought it was green for a long time, and then we had high subsidies, and we actually made it, and we do that a lot. And if you go to Brazil, we have a sugarcane to biofuel all the time, and it will be a big player for the future in Brazil and unique locations like that. Corn to ethanol, depending on how you do it, it can be green. We just didn't know at the beginning. We did not do life cycle analysis with the right system boundary to understand where we are paying for environmental fee, right, in this whole setup. So going back, that's why a lot of people are doing life cycle analysis on CO2 utilization. So that don't go down to this particular path because that doesn't make sense, but let's go to here. So in my even technology, when I develop, it's not only even looking at huge picture. When I look at the reactor 1, 2, 3 connected, or separator 1, I connect them together. I do life cycle analysis of this overall system before even going bigger. Then I know this reactor is very efficient. This reactor is not as efficient, but you can say this really efficient reactor has the highest carbon footprint, then I adjust that. So now what we need to do is then not only try to make the most efficient material, pure material, but at the same time, what is the lowest carbon or environmental footprint? And by doing so, we're not going to get into trap of early failure of corn to ethanol.
Well, we have to cut this wonderful discussion here short today. Thank you very much, Alissa, for your wonderful talk.
Thank you. Thank you.